Right. I think the last thing that we spoke about when we were still in school was reaction rates, or we sort of introduced you to reaction rates where um, we defined rate of reaction. We looked at a number of factors that affect rate of reaction and all that. Now we're going to talk about something a little bit different, but it's under chemical change, and this is equilibrium. So with equilibrium, we're going to explain what chemical equilibrium is, and we're also going to talk about a few factors that affect equilibrium. So let's look at a few definitions from your exam guideline. Right, one of the definitions you need to know is you should be able to differentiate between an open system and a closed system. For example, if you look at this setup that we have on the screen, you can clearly see that we are looking at an open system. Why do we say the system is open? It's because this reaction that is occurring here is in contact with the environment. So we can have things going in, we can also have things going out. So as this reaction progresses, you find that the gas that is being produced is going to escape. And that means this is an open system. Right, so we say an open system will continuously interact with its environment. And if the system is closed, then it will not interact with its environment. For example, if I decide to close, we put a rubber stopper here and we close this system. Then we now say it is a closed system. Nothing is going in, nothing is going out. So for us to be able to define and to work with equilibrium, for me to get to what is equilibrium, I need to be able to explain one of these things. You need a closed system. The system has to be closed. If the system is not closed, there is no way you are going to reach equilibrium, or there's no way you are going to attain dynamic equilibrium. Then number two, you need a reaction that is reversible. You need a reversible reaction. We call it a reversible reaction. But one might be asking, what is a reversible reaction? Okay, a reversible reaction, if we look at this particular question that we were dealing with, they were having hydrochloric acid and calcium carbonate. So calcium carbonate was reacting with hydrochloric acid, and it was giving us calcium chloride and some water and carbon dioxide. If you look at this reaction, there's one arrow here. It's just going straight. These two are combining to give these three products. This one is not a reversible reaction. A reversible reaction is one in which these products can then also be converted back to reactants. For example, the Haber process. If you have nitrogen reacting with hydrogen to give us ammonia gas. The ammonia gas can also disintegrate to give us hydrogen and nitrogen. We call this a reversible reaction. So for us to attain equilibrium, these are some of the conditions we need. We need the system to be closed. If a system is not closed, there is no way we are going to reach equilibrium. And the reaction needs to be reversible. You cannot have equilibrium here with this reaction, which is just going to go, the calcium and the hydrochloric acid are going to react until one of them is finished. In this scenario, the reactants are not going to be completely finished, because the moment they start making ammonia, the ammonia would also start breaking to form hydrogen and nitrogen. So that brings us then to what is chemical equilibrium. This is a dynamic equilibrium. When we have chemical equilibrium, we say this is a dynamic equilibrium in which the rate of the forward reaction equals the rate of the reverse reaction. So that means the rate at which nitrogen and hydrogen are combining to give ammonia is equal to the rate at which the ammonia is breaking to give the hydrogen and the nitrogen. So some reversible reactions, they will the reactants will react. As they react, the products will start breaking down until we reach a dynamic equilibrium in which the rate of the forward reaction will equal to the rate of the backward reaction. It does not mean the reaction has stopped. Remember, when we're doing reaction rates, our graph, maybe if I was measuring the amount of carbon dioxide that is produced here, it will increase sharply at the beginning, then it will level out, signaling that at this point, the reaction has stopped. Now, that's a different case with equilibrium constant. With equilibrium constants, so if I'm to start on the graph with, let's say this is our graph, I'm to start with hydrogen, that much of hydrogen maybe, and that much of nitrogen there. Maybe let me use different colors. What we're going to see is the hydrogen will start to decrease.
Sir,
yes?
We can't see the screen.
You cannot see the screen?
It's not clear. Like it's not the whole thing.
Oh. How about now?
It's still the same.
Still the same?
Yeah, now it's fine, sir.
Is it fine now?
Yes.
All right. Okay, that's fine.
Thank you.
Okay, so as the hydrogen starts reacting, we're going to have a decrease in the hydrogen. Because also nitrogen is also reacting with the hydrogen, we're going to have a decrease in the nitrogen. But remember, sorry, let me use a different color here. Remember, the nitrogen is decreasing also. And as soon as they start decreasing, they are also making ammonia. The ammonia, this is our ammonia, NH3. The ammonia is also going to start increasing. But they'll get to a point where the rate of that forward reaction equals the rate of the backward reaction. So we'll get to a point like that. Let me use the same colors again. And the nitrogen and our hydrogen. So at this point where they level out, it does not mean the reaction has stopped. It simply means that the rate of the forward reaction is equal to the rate of the backward reaction. And at this point, we say we have reached equilibrium. We have reached equilibrium. Right. And now, there are a few things that can affect equilibrium. There's only 3 things that you need to look at that can affect equilibrium. And we're going to talk about them now. So let me just remove this here and introduce another one. So this is the questions on equilibrium. This is the type of questions that they will ask you on question 6. So a few things that we need to know. If we look at this example that I've used, question 6, as you can see, we have a reaction here. We have this reaction. And you can see it's a reversible reaction. I can see with this double arrow, the top arrow is saying forward reaction, the backward is saying the one that points in that direction is the backward reaction. And they're saying a closed container. So we have the closed container, we have a reversible reaction. That means we can actually reach dynamic equilibrium. Then there's this statement. I'm going to talk about this statement. They're saying delta H is less than 0. That means delta H is negative. Now, if delta H is negative, what does that mean? It means that the forward reaction, let me repeat that part. If delta H is negative, it's telling you that the reaction is an exothermic reaction. That means heat is being given off. But which reaction is giving off heat? Is it the forward or the backward? If it's written like this, it means the forward reaction is an exothermic reaction. That means when A combines with B to give C, it also gives off heat. That is the forward reaction. That is the exothermic reaction. And what it means is when C disintegrates, into A and B, it requires heat. That means the backward reaction is going to be endothermic. So the forward reaction in this case is exothermic, the backward is endothermic. Right, I've seen it from this sign. If the sign, they say delta H greater than 0, then that means the forward reaction is the one which is endothermic and the backward is the one which is exothermic. Why is this important to know? Because when we talk of those three factors that affect equilibrium, one of those factors is temperature. Now, what is temperature? Temperature is average kinetic energy. And we can say every time we're talking of temperature, if the temperature has to increase, you need to add heat. If temperature has to decrease, you need to remove heat. So when we talk of temperature in this scenario, think of heat. So one of the things that will affect equilibrium is temperature. That's number one. Now, temperature is going to affect equilibrium. Another one which will affect equilibrium is concentration. We'll explain how it affects equilibrium, just remember them. And the last one is going to be pressure. This one only applies when the reaction has gases involved. If there's no gases involved, we're not going to worry about the pressure. Right, now when we look at our reaction, this one that we are working with, there's one thing that we also need to sort of speak about before I can tell you how temperature, concentration, and pressure affects equilibrium. We need to be able to calculate what we call an equilibrium constant. And an equilibrium constant is just a number. It does not have units, but it shows you what you have more than the other one. So when we reach equilibrium, you might find that you've got more reactants than products, or you've got more products than reactants, and the Kc value is an indication of that. If you have a bigger Kc value, as you're going to see now, it will tell you something about that equilibrium. If you have a very smaller Kc value, it will also tell you something about that equilibrium. So if I'm to calculate the Kc value, right, we call it Kc, it's an equilibrium constant. Now you see I put a K for constant and C stands for the concentration. So we're going to be dealing with the concentration of what is in the equation. Now remember, when you talk of concentration, can I give the concentration of a solid? I know it's 1. Can I give the concentration of a liquid? I know it's 1. So you already know if we are dealing with a solid or a liquid, their concentration is going to be 1. So sometimes we just omit it when we write the equation. Right. In this case, we're going to say, let me just show you how you calculate the Kc. Every time you calculate Kc, you just say Kc is equals to the concentration of products over concentration of reactants. So that can simply tell you that this is more of a ratio of how much of the products you have compared to the reactants that you are having. So in this case, I'm going to look at my reaction. I've got 2 of A in gas, 3 of B in gas, and 2 of C in as a gas. So that means all of them are going to be involved when I calculate my Kc. In this case, when I calculate my Kc, I'm going to take the concentration of my products. In this case is the concentration of C. And this number that is in front of C, I say to the power of 2 over the concentration of your products in this, sorry, of your reactants. In this case, concentration of A to the power of 2. Multiply it by the concentration of B to the power of 3. Right, let me slow down here and use another example. Let's say I had 2A plus 3B to give us 5C plus 6D. How was I going to calculate the equilibrium constant for this one? I would say Kc is equals to the concentration of the products C to the power of 5 multiplied by the concentration of D to the power of 6 all over concentration of A to the power of 2 multiplied by concentration of B to the power of 3. So it is very important before you calculate the Kc to first check if your equation is balanced. If your equation is balanced, it will help you to calculate the Kc, because you're going to need those numbers that are in front of your reactants and in front of your products. But this can, if and only if this is a gas or in aqueous form, you don't include pure liquids. You don't include pure liquids. You don't also include solids. Ne? Right. So I'll do other examples later on. So when we calculate this Kc, this, remember the value you are going to get, if it's, and you can see this is a fraction. Ne? This is a fraction. So if the value is greater than 1, that means you're having more products than the reactants. But if the value is less than 1, that means you are having more of your reactants and less of your products. So we are saying the equilibrium, if it's greater than 1, we're saying the equilibrium lies more to the products. Less than 1, the equilibrium lies more to the reactants. That's how we describe it. Now, how does temperature affect equilibrium? Like in this case, where we are having an exothermic reaction as the forward reaction and an endothermic as a backward reaction. This is where we use Lee-Chatelier's principle. I'm sure you have read of it, or you are going to read of it. If you have not yet read of it, but it's there on our exam guideline. And Lee-Chatelier's principle simply just, he came up with a principle to say, if a system is at equilibrium, that means the rate of the forward reaction equals the rate of the backward reaction. So there's that balance, that equilibrium. When a system is in equilibrium and a disturbance is introduced, the system does not like that disturbance. The system is going to react in such a way that it counters that disturbance. How does it counter that disturbance? It favors the reaction that cancels that disturbance, or it favors a reaction that counters that disturbance. So let's look, for example, here. If, let's say, someone decides to increase the heat, so you increase temperature on this closed system. So we have this closed container, it's all sealed up, and then you start heating it up. Remember, this reaction is already producing its own heat because, sorry, the forward is already producing its own heat because it is exothermic. Then you start heating the reaction. You add heat. What it means is you have increased the heat, and the system does not like that increase in heat. So what is the system going to do? It is going to favor that reaction that removes the heat from the system. And which reaction removes heat from the system? It is the backward reaction. So the backward reaction is going to be favored. The reverse reaction is going to be favored. That means you are going to have more of C breaking down to give you more of A and more of B, because you have favored the backward reaction. So if I heat the system, that means I've introduced more heat. And this system does not like this heat, this disturbance that I've introduced. So the system is going to react in such a way that it wants to take away that heat. And the only way it can take away that heat is by favoring the reaction that actually uses up heat. And the reaction that uses up heat is the endothermic reaction. In this case, the reverse reaction. So more of C is going to break down to give A and B. So what you're going to have is that that equilibrium is going to be disturbed. C is going to decrease. That means the concentration of C is going to decrease because you favored the backward reaction. So it's going to decrease, while the concentration of A is going to increase and the concentration of B is going to increase. So we say our equilibrium now shifts from the products towards the reactants. our equilibrium is going to shift from your products towards your reactants, and this will affect this Kc value. It is going to affect the Kc value. Temperature is the only factor that affects equilibrium, and at the same time also affecting the Kc value. So in this case, if we add heat and we have more of C breaking down to give more of A and more of B, that means you now have more reactants than products. So your Kc value is going to decrease. Right, what if I decide, instead of heating it, I decide to take away some heat? So we cool it down, we put it in the fridge, or we put it in the freezer. That's taking away heat. What is going to happen? As you take away heat, this system does not want you to change the heat that it has. So you are taking away this heat. It wants to replace that heat. If you take away some, it wants to replace that heat. And the only reaction that can replace that heat is the forward reaction. So more of A and more of B will combine to give more of C. You will favor the forward reaction so that you can replace the heat that has been taken away. Now that means you're going to have a decrease in A and a decrease in B, and you're going to have an increase in C so that you can produce more heat. What it means is you are now having more products than reactants, and the Kc value will increase. Your equilibrium will shift towards your products. Right, it looks like we're not going to have enough time, and I feel like I've been talking for a very long time, and they're already telling me I'm running out of time, and I only have 10 minutes, which is fine. Now, what does that mean? It means, just remove this. Right, so that's how temperature affects equilibrium. I think the next lesson will talk of how to calculate this equilibrium. We'll go into detail, but you can already start calculating the Kc, and the Kc can only be calculated when a system has reached equilibrium. The other thing that affects equilibrium is concentration. How will concentration affect equilibrium? For us to explain how concentration affects equilibrium, we need to go back to Le Chatelier's principle again. Remember, any disturbance that is introduced to a system at equilibrium, the system wants to cancel that disturbance. So for example, when you increase concentration, in this case, I'm just going to say, let's increase concentration. Let's say we have this system at equilibrium, and we increase the concentration of reactant A. So we come here, we decide, let's add some more of A. So we increase more of A. What is the system going to do? The system does not like that increase of A. It wants to cancel that increase you have made. So what is it going to do? That system is going to favor the reaction that uses up A. And the reaction that uses up A is the forward reaction. So as the forward reaction is favored, look at what is going to happen. As you favor the forward reaction, obviously you are going to increase more of C. So there's going to be an increase in C. But what is going to happen to B? B will gradually decrease because that extra A you have added is going to combine with more of B to form more of C. So if I add an extra 2 here, maybe one of it is going to react with one of B. So we're going to have a decrease in B, and we're going to have an increase in C. So how does it look like on a graph? What I've just explained on concentration. Let's say this was your A, and this was your B, and this is our C. A has decreased to that level, and B has decreased to that level, and C has increased, and they have reached equilibrium. So someone decides to be funny, they introduce more of A. That means you're going to have a sharp increase in A. That has disturbed the equilibrium now. Now, if this has disturbed the equilibrium because you have just introduced A, you have opened the container somehow and put in some of A. The system does not want this increase in A. So it will favor the forward direction. By favoring the forward direction, it will use up that extra A. So you will see another decrease now in the A was being used up so that we cancel that increase. But we're not going to use all of it until we get here because you have introduced more of it. Remember, the moment that A is decreasing, it's combining with B to form C. So you're going to have an increase in C, a gradual increase in C. And because the A is combining with the B, you're also going to have a decrease in B. And what will happen is you establish a new equilibrium again. You establish a new equilibrium again. But what you have done in this case is that you have shifted that equilibrium towards your products. But that does not change the Kc value because this system is going to establish a new equilibrium. It is going to establish a new equilibrium. And that new equilibrium, if you calculate that Kc, it will still be the same Kc value as the other one. Remember, you're taking from somewhere, putting somewhere, so they're going to strike another balance. It's different from the one for temperature, where you have completely shifted even the concentrations. Ne? Right. That's how, okay, maybe I must use one to explain a decrease. So allow me to just use the same diagram and say, what if one decides on this system it's at equilibrium, instead of increasing, right, instead of increasing A, what if someone comes and says, we want to take out the products. So they take out this C. We decrease it. We take out the C. In other words, we decrease it. Now, if that concentration is decreased, what is going to happen? Ne? What is going to happen? You are going to have a sharp decrease in C like that. But the system does not like its C to be decreased. So you are going to also favor the forward direction to replace that C that has been taken out, so that C can gradually increase. But what is going to happen to A and B? That means more of A and more of B are going to react to give that C. So you're going to have a decrease in A and B until you reach another equilibrium. That's how you affect equilibrium. Right, I don't think I have enough time here. You're telling me 10 minutes and all that. So I'm left with explaining pressure. Pressure is better explained with this one that we have, because remember, this is a gas, this is a gas, and this is a gas. With pressure, don't worry. Just look at it the same way we're looking at rates of reaction. The same way we're looking at rates of reaction. How many moles of gas do we have on the reactants? There's 2 plus 3, there's 5 moles. So that means we've got 5 volumes. That means the reactants occupy a bigger volume compared to the products, because there's only 2 moles. That means 2 volumes. So what are you going to do now? If you increase pressure, remember, if you increase pressure, according to Boyle's law, the volume needs to decrease. So if you're increasing pressure, you are decreasing the volume. So if I increase pressure, I've decreased the volume. And this system is going to feel as it has been put under pressure. So it's going to favor a reaction that helps it relieve that pressure. Now, if I increase pressure, that means I'll favor the one with a smaller volume. That means the forward direction will be favored by an increase in pressure. More of A and more of B will combine to form C, which has a smaller volume. If I decrease pressure, that means I have a bigger volume. That I will favor the backward reaction. That will increase. That will mean I will produce more of A and more of B with a greater volume. Let me just check quickly here how much time left. They're saying, okay, we've got 1 minute, and today I don't think they are going to increase my lessons. Any questions? I think I'll be able to take only 1 or 2. Then I'll post some work and a video with calculations on Classroom. Any question? Nothing. Kathleen?
Sir.
Yeah. How was it? New topic, new everything, not making sense.
Yeah, no, it's not making sense.
Okay, just go through the video. I'm going to ask if they can post it on YouTube. Then I'll post another one with some calculations. I know this one was really fast. I'll break it down into 10-minute videos for you.